Hey everyone, it's Justin again. In this lesson, we're going to continue working with slope-intercept form of linear equations and discuss how to write a linear equation in this form using given information. Let's get into it. Let's take a moment to review what makes up a slope-intercept form equation. In the equation y equals mx plus b, what do we need to know to define a specific line? We need to know what m and b are. X and y will still be variables. So what do m and b represent? M is the slope, and b is the y-intercept of the line formed by the equation. So in order to write the equation of a line in slope-intercept form, we just need the slope and the y-intercept. But how do we get them? Let's start with slope. There are a few ways that we've learned to define slope. How do you like to think about slope? Maybe you thought of how, on a graph, we think of the rise over run between points. Or maybe you remember the slope formula that we can use with two coordinates, y2 minus y1 over x2 minus x1. My favorite way to think of slope is the change in y over the change in x. Remember that we use this triangle, or delta, as shorthand for change. All of these are correct, and they all work, but some of them will be more efficient than others depending on how you're presented with the information. If you think about all the ways we can represent functions, there are a bunch. The most common ones you'll see for linear functions are graphs, vertical tables, sets of coordinates, and horizontal tables. We'll be looking at all four of these to see the best way to find the slope within each. Use the organizer in your notes to follow along, and feel free to pause the video anytime you need to. Let's start with graphs. What do you think is the best way to find the slope of a line on a graph? Since graphs are such a great visual, it's most efficient to pick 2 points on the line and count the rise and run between them. In this graph, between these 2 points, I am rising down 2 and running right 1, which makes the slope -2 over +1, or just -2. Let's take a look at vertical tables. Here, this left column represents the x coordinates, while the right column represents the y coordinates. And each row in this table represents a combination of x and y that creates a point on the line. What do you think is the best way to find the slope from a table like this? You absolutely could pick 2 of these rows and use the slope formula, and that would work. Or we could think of this as the change in y over the change in x. To find the change in y, I can just look from the y in one row to the y in the next and see how it changed. In this case, to go from 0 to 6, y increases by 6. To find the change in x, I could do the same thing. To go from -4 to -1, x increases by 3. If I put that change in y over the change in x, that makes a slope of 6 over 3, or 2. If I check the rest of the changes in y and x, you can see that they all look different. But because the fractions are all equivalent, this is a steady slope. Even though all the points on this table only represent some of the points on its line, the slope going between 2 of them will always simplify to be the same if this is truly linear. There are 2 more representations left to look at. Pause the video here and see if you can figure out the most efficient way to find the slope from a set of coordinates and a horizontal table. Looking at the coordinates first, we could use the slope formula. Or, just like with our vertical table, we could just take a look at how the x and y coordinates change from one point to another. For these first 2 points, the x-coordinate goes up by 1, and the y-coordinate goes down by 2. If we put those together into the slope, it's -2 over 1, or just -2. And no matter which points you pick, even if the slope doesn't look identical, it should be equivalent and simplify to match this. The horizontal table is really similar to the vertical table. I bet that whichever method you find you like best on a vertical table will work just as well on a horizontal table. In this case, I'm going to pick two columns in this table and then check how the x and y coordinates change from one to the next. You don't have to use the first two, or even two that are next to each other. So I'm going to use these to switch it up a bit. The change in x here is plus 3, and the change in y is plus 6. I just have to be really careful putting my slope together because in the slope formula, y has to go on top and x has to go on the bottom, which is the opposite of how they're presented in this table. So my slope here is 6 over 3, or positive 2. Now, there is something very important to check when you have a table or set of coordinates, and that's whether or not your points are actually linear. On a graph, you can see whether they form a straight line, but it's not quite as obvious in other representations. Instead, you need to make sure that the slope between each point is equivalent. We also call this a constant rate of change. Take a look at this table. From the first row of coordinates to the next, x increases by 3 and y increases by 4. That makes a slope of 4 over 3. From the second to the third row, x increases by 6 and y increases by 8. This makes a slope of 8 over 6, which simplifies to 4 over 3. From the third row to the fourth, x increases by 4 and y increases by 6. Uh-oh. That makes a slope of 6 over 4, or 3 over 2, which is not equivalent to the others. So this table does not have a constant rate of change. This means that these coordinates do not form a straight line or are not linear. So it wouldn't be possible to write an equation for them in slope-intercept form. Keep this in mind whenever you're asked to write an equation for a set of points. In fact, let's go back to those same representations we were analyzing earlier and make sure that the slope has a constant rate of change. I mean, unless we are told that the data represents a linear relationship, we really should make sure. I'm definitely seeing a constant rate of change on this graph. The slope simplifies to be -2 everywhere on here. And since a graph is a visual representation, we can even just look and see that it's reasonable to say this is a straight line. We saw earlier that anywhere we calculated the slope in this table, we got the same answer. So it's definitely safe to say that this is linear too. When using the coordinates, you may be tempted to just use 2 points, find the slope, and move on, but we have to make sure that the slope is constant among all the points we have. And it looks like it is. It always simplifies to be -2 here. Finally, let's double check that this horizontal table shows a linear relationship. We already calculated that this slope is 2, but we can verify that this is true and we include every point somewhere in our calculations. This looks like the slope is turning out to be 2 no matter what, meaning this also has a constant rate of change. All right, now that we know how to find the slope and to make sure our data represents a linear relationship, we'll need one more piece of information to write the slope-intercept form equation, and that's the y-intercept. What is a y-intercept? We've really only learned 2 ways to think about y-intercepts. Maybe you're thinking of it as the point where a line crosses the y-axis. That's totally true, but for identifying a y-intercept, this will really only work from a graph. What do the coordinates of a y-intercept look like? Because it's on the y-axis, its coordinates have to be 0, something, or since we use b as the variable for the y-intercept, we could say that the coordinates are 0, b. With this in mind, take a look at these same 4 representations of a linear function. Pause the video here and identify the y-intercept in each. Starting with the graph, we know to look for the y-intercept along the y-axis. It's here at 0, -3. In the vertical table, we're looking for a point that is 0, something. Ooh, there are 2 rows that have a 0 in the coordinate. But don't be fooled. This one is the y-intercept, since it would be 0, 8. This top row would actually be the x-intercept, but we don't need that. In the coordinates, we're also looking for one that is 0, something, which would make our y-intercept 0, -3. Last up is the horizontal table. Make sure you find the x-y pair where x is 0. In this case, that would be 0, 8. For each of these representations, we now know their slope and their y-intercept, which means we can put them together to write their equations in slope-intercept form. Writing the actual equation is just a matter of substituting the slope for m and the y-intercept for b in the slope-intercept equation. So pause the video here and try writing these equations on your own now. For the graph, the slope is -2, and the y-intercept is -3. So I'll put in -2 for m and -3 for b. It's never good math grammar to have a sign and an operation next to each other, so I'll rewrite this as y equals -2x minus 3 instead. The coordinates have the same slope and y-intercept, so their equation is the same. How about for the tables? With a slope of +2 and a y-intercept of 8, that makes the equation y equals 2x plus 8. And that's all there is to it. When it comes to writing equations in slope-intercept form, you need to find the slope and the y-intercept from the information you've been given. Be on the lookout for the different ways that you can find them depending on the way the information is presented. And unless you already know that the points are linear, make sure that there is a constant rate of change between all points before trying to write the linear equation. After all, if the points aren't linear, then there can't be a linear equation that represents them. Once you finish up your guide and notes for this video, you should move on to the Mia's puzzle practice activity in your PDF. This activity gives you more practice with feedback to make sure you're ready for the online practice game. And finally, you'll complete the practice game. Good luck with all that, and I'll see you next time.
Hey.